Hi scholars, today we're going to talk about solving equations. So this will likely be a review from 7th, 8th, and 9th grade. So we'll go through it fairly quickly, and we're going to introduce this sort of a different way of looking at how we can solve equations, a way where we use structural features of the equation. So, for example, solve the equation negative 3k minus 15 equals 18. Okay, so we can do this by applying inverse operations to isolate k, right? Basically, when we're solving equations, this right here is a linear equation. So we have a variable that's an unknown, and we want to do a bunch of stuff, and we want to end up with, at the bottom, with k equals, right, something, right? That's our goal. Okay, so I like to, when I solve equations, I like to find the equal sign, and then just sort of put a dot down the middle so I remember where it is so it doesn't get lost somehow. Okay, so our first step is let's get rid of this constant, this negative 15. So the minus 15 is the same as negative 15. So how can I get rid of a negative 15? Well, of course I can add 15. If I do it to one side of the equation, I got to do it to the other side because I don't want to change the value, right? I want to keep everything the same. What's nice about using inverse operations is that these cancel, right? This is just 0. So all I have left on this side of the equation now is a negative 3k. And I still have an equal sign here, and 18 plus 15 should be 33. And so it's just one more step, right? Negative 3k, I want to divide by negative 3. That's the inverse operation, inverse of multiplying, right? So there's an invisible multiplication between the negative 3 and the k. So to get rid of that, let's divide. And so I'm going to do the same thing here, divide by negative 3. And just the same way 15's canceled out here, our negative 3's cancel out here, and all I'm left with is exactly what I wanted, which is k equals 33 divided by negative 3 is negative 11. And this right here is an answer. Now with any equation, you always want to check your work, right? Just to make sure you didn't make any silly mistake. And so we can do that by plugging in the value of k that we found into the original equation, right? So negative 3, right? This is really saying negative 3 times times negative 11 minus 15. Does that equal, right? This is my check. Does it equal 18? I don't know if it does. This is my check. And when you do the math, you in fact will find out this is 33 minus 15. It does equal 18. So your check works, right? So that is the correct answer. So that's how we've been solving equations for quite a while. There are other ways of doing it, right? They may seem like just slightly different, but they will be more and more useful later on as we get into more and more complicated algebraic expressions. So another way of solving equations is solving equations using structure. And what does that mean, structure? Well, structure is sort of like the form of an expression. It's how the expression is put together. Okay, so let's just take a simple example. I have 2 times the quantity, k plus 5, right? It's in parentheses, so it's that whole thing, equals 18, right? Solve for k. So there's a couple different ways we could do this, right? One way is we could, if we wanted to, distribute, right? End up with 2k plus 10 equals 18, then subtract 10 from both sides, then divide by 2. You would get the answer. It's no problem, right? It's a simple problem. So that's one way of doing it, is distributing. Is there another way of doing it? Well, there is, okay? So let's try to solve this equation by making the form of the right side of the equation look like the left side of the equation. So the left side of the equation looks like 2 times something, okay? Let's make the right side of the equation look like that. Instead of 18, can I rewrite that as 2 times something? Yeah, 2 times 9, okay? Now, because this 2 and this 2, it's the same, right? They're the same, 2 times something, the same form. We can ignore them, right? I mean, essentially what you're doing is dividing each side of the equation by 2, but we can also just reason about it and ignore them and say that if this equation is true, it must be true that k plus 5 equals 9, right? In other words, that k equals to 4. Which, yeah, you would have gotten it as well by distributing, right, and solving, like maybe one more step. But this is another way of thinking about it. Now, using structure, this is nice because sometimes you're actually able to solve sort of complicated looking equations entirely in your mind using mental math by using this kind of reasoning, okay? So this is pretty cool. So we're dealing with, we just solved a few equations. So let's ask sort of a broader question. Are equations always true, sometimes true, or never true? Well, this is a broad question, right? And the answer is, it depends. Some equations are always true. Some equations are never true. And some equations, for example, like the last two equations that we did, right? These equations are sometimes true. This equation is sometimes true. It is true when k equals negative 11. It is not true when k equals 4 or 7 or any other number, right? It is only true when k equals negative 11. So that's sometimes. Some of the time it is true, right? This equation is only true when k equals 4, not true of any other value of k. So we know what it looks like for an equation to be sometimes true. These are, we can call these sort of solvable equations, right? So any equation where you can say, yeah, x equals 3 or whatever at the end, right? Solvable equations. Okay. What would it look like for an equation to be, well, let's start with this one, never true. What would that look like? Well, let's start out with an equation that is never true. 0 equals 1. Is that ever true? Never true. Okay, that's fine. So we can actually use this idea, 0 equals 1 is an equation that's never true. I could also write this as the same idea as x equals x plus 1. This is another equation that is never true because there is no value out there that it's the same if you have that value and is identical, the same if you take that value and add 1 to it. There's not a number out there for which that property holds, okay? So here's a couple examples that are never true. What about equations that are always true, okay? Well, we can use factoring to find equations that are always true. 3x plus 6 equals 3 times x plus 2. Yep, this is always true. This is true if x equals to 1. If you plug in 1, I get 9 equals 3 times 1 plus 2, 3 times 3. Yep, it's true when x equals 1. What about when x equals 5? Okay, 3 times 5 is 15, plus 6, 21. Does 21 equal 3 times 5, 7? Yeah, 3 times 7 is 21, right? It's true for x equals anything you want, right? Any number at all. So this is an example of an equation that is always true. Okay, so just because you have an equation doesn't mean that you're always going to be able to solve for x, right? In this particular example, if you tried to solve for x, you would end up getting 0 equals 0. You can try it yourselves. And when you get something like that, that's a good indication that the equation is always true. It doesn't matter what value of x it is. And this is sometimes called, equations that are always true are also called identities. And when we learn a little bit later in trigonometry, we're going to learn about some really important trigonometric identities. Okay, let's take a look at one more example. Let p equal 5 minus 2m, so p equals 5 minus 2m, and let q equal m plus 29. Okay, this is what we're starting with. Looks like a pretty strange question, but we can follow it. We can keep going, right? If p equals q, then what is the value of m? Okay, so there's a lot going on in this problem. However, the question is really saying that if this is the same as this, and this is the same as this, and this is the same as this, then what is m, right? Solve for m. This is what the question is asking. What does m equal, right? There's an m, there's an m, there's an m. Okay, so we can solve this pretty easily just by setting p equal to q, right? It's sort of like a transitive property. I know that p is nothing more than 5 minus 2m, right? So I just substitute that in. And I know that q is nothing more than m plus 29, right? And then the question is saying solve for m. So I can do that pretty easily. This right now is just another couple step equation. So let's do it. Let's add 2m to both sides so we can get m's all on one side of the equation. I like to draw my dotted line. I end up with a 5 on this side of the equation equals 3m plus 29. Let's subtract 29 from both sides, right? Basically a pretty simple two-step equation now. So I have 3m equals 5 minus 29 should be negative 24. Divide by 3, you end up getting that m equals negative 8. And that is how you solve this problem. Have a great week.